My name is Masai Kimi from the Institute of Statistical Mathematics. In this talk, I will explain these concepts which have been proposed recently, and I will explain how estimating function, which is used in statistics, induce these geometric structures. And before that, I make a brief mention about statistical manifolds and concept functions, just to remind you. Maybe most of you are familiar with statistical manifold and concept function, but just to remind you, I will explain. Statistical manifold is a triplet of the differential manifold M and Riemann metric G and torsion-free affine connection nabla, which satisfy that nabla G is totally symmetric. This condition is equivalent to the dual connection of nabla star is torsion-free. The dual connection is defined by this relationship. And in this case, M triplet of the M, G and nabla star is also statistical manifold. And if nabla and nabla star equal to each other, then the nabla is a Leibniz-Vita connection. And the contrast function is a two-point function defined on M, which satisfies these conditions. And here, this notation is a bit unusual notation, but maybe it is well known in the information geometry. These are the vector fields, and this means, for example, the vector field X play a role to differentiate the function rho with respect to the first argument P, and Y also play a role to differentiate the function rho with respect to the second argument Q, and then the value is evaluated on the diagonal set. So, roughly speaking, the second condition means that the first derivative at the point on the diagonal set is 0, and the third condition means that a second derivative gives the Riemann metric. And if these conditions are satisfied, then at least locally this condition is satisfied. And from a contrast, once we get define the contrast function, then we obtain the two affine torsion-free affine connection nabla and nabla star, which are mutually dual with respect to the Riemann metric G by these relationships. And then these affine connection torsion-free, so these triplets are both statistical manifolds. A typical example of the contrast function is maybe the Kullback-Leibler divergence. Here, M is a parametric statistical model, which is a set of probability density functions indexed by the d-dimensional parameter theta. And then the Kullback-Leibler divergence defined as follows in this way. Then, by taking the first derivative with respect to the parameter, then we obtain this equation. Then if P and P1 equals to P2, then this vanishes. And taking from the second derivative, well-known Fisher metric is obtained, and from the third derivative, we obtain the E connection and M connection. Now, I explained the statistical manifold admitting torsion. Statistical manifold admitting torsion is also a triplet of differential manifold M and limited metric G and affine connection nabla. But in this case, this possibly has a torsion. Then this triplet is statistical manifold if and only if this equation holds. And this condition is equivalent to the condition that nabla star is torsion free. And if here T is a torsion tensor field of nabla, so if nabla is a torsion free, then this condition reduces to the definition of the statistical manifold. But we should note that in this case, the triplet M and G and nabla star is not necessarily a torsion statistical manifold. This is different from the statistical manifold in the case of the statistical manifold. And precounter function was proposed by Dr. Matsui over there. This is a this is a function defined on a tangent band. Defined on a direct product of tangent bundle and the manifold M, and this is called the precounter function on if and only if these conditions are satisfied. And this notation is very similar to the notation used in the definition of the constant function, but the difference is here that vector field D, the load of the different vector field D is defined in this way, yes. The first condition is just linearity of the first segment, and then these conditions are almost similar to the to the case of constant functions. And a typical example of the okay, so if we have a constant function, then the first derivative of the constant function is automatically a pre-constant function. So this concept is can be seen as a generalization of the derivative, first derivative of the constant function. And if we have once the pre-constant function defined on the manifold M, then in a similar way, two affine connection nabla and nabla star are defined by the same equation as in the case of the constant functions. And here, nabla and nabla star mutually zero with respect to G, but and nabla star is always torsion free, but nabla is not necessarily torsion free. This is a difference from the case of constant functions. If the rho is a pre-constant function on M, then the triplet M, G, and the nabla is a static manifold of torsion. So from now on, we call this static manifold of torsion just S-mat. We call S-mat just for short. And now we go to the notion of estimating functions. Estimating function is okay. So now we consider in the framework of this parametric model. M is a parametric cycle model, and x1 and x2 is a random sample from some distribution P. And estimating function is the function of the defined on the function defined on the sample space diagonal set direct product of the sample space and the parameter space, and this is a condition to for the estimated functions. Then if we have some if we are given some estimated function, then we construct the estimating equation. Then by solving this estimating equation, we obtain the M-estimator as a solution of this estimating function. And under some regulatory conditions, this estimator has a consistency and asymptotic normality and asymptotic variance covariance matrix given by this sandwich form. And in order, from now I'll explain how the estimated function induces the statistical manifold torsion. But in order to define such a geometric structure, we need a concept of standardization. Standardization is okay. So now we have some estimated function. Then for this estimated function, the standardization is defined as this equation, and this standardization has a geometric interpretation. This here. So the standardization of the estimated function u star is obtained by the orthogonal projection of the score function s onto the linear span of the each element of the original estimating functions in this Hilbert space. And standardization, if we consider standardization, then the estimator from the estimating equation is the same. So in this sense, these estimations are equivalent. And but asymptotic variance covariance matrix also the same, but the form is a bit different. We can rewrite the variance covariance matrix of this estimator, just matrix G. So if we use a standardization, then the single variance covariance matrix can be written in the similar form to the Fisher information matrix. So this is sometimes called the Godin information matrix. Now we consider now I'll explain how the estimating function induces the statistical manifold admitting torsion. In order to do that, we go back to the Kuiper-Gleiber divergence. Kuiper-Gleiber divergence is a contrast function. So by taking the first derivative of the Kuiper-Gleiber divergence, we obtain the pre-contrast function. And here S is a square function. So if we are given an estimated function u, then if we replace this square function with the estimated function, we expect that we can obtain the predicted function, but it's not necessarily true here. But if we replace the score function, this score function, with the standardization of the original estimated function, then we can obtain the pre-contrast function. And because if you use standardization, then this is a defined pre-contrast function without depending on the choice of the coordinate system. So, in this sense, considering the standardization is natural. And then from this pre-constant function, we can obtain the statistical manifold, the structure of the statistical manifold of S-mats, and in this way. This is a pre-constant function. Then from the unbiasedness of the estimate function, then we obtain this is a second condition to define in the definition of the pre-constant function. Then the Riemann metric can be calculated like this. And this is a Riemann metric is given by the Godamba information matrix. And Dirac connections, the coefficient of the Dirac connections calculated like this. This form is very similar to the E connection, the M connection, but the difference is here. This part is different from the EM connections. And here we should note that nabla star is always torsion free because this relationship holds. And but nabla is not necessarily torsion free unless the standardization of the U is integral with respect to theta. Okay, how much? Okay. 5 minutes, okay. Now we consider, okay, so this in the information geometry, in the Dirac space, we can define canonical divergence, nabla divergence, using the Dirac affine coordinates like this. And this divergence is can be defined expressed in terms of the Dirac affine coordinate, but this by taking this with the first derivative of this function, then we obtain the pre-constant function. But the pre-constant function can be written in the coordinate-free form like this. And here, gamma star dot means gamma star is called nabla star geodesic, and nabla star gamma star dot is a tangent vector at the point here. Okay, so anyway, the pre-constant function can be written in this form. So from this observation, we define the pre-constant, canonical pre-constant function in the space of partially flat space. Partially flat space means that this one, that is okay. So yeah, now is nabla has a possible torsion. So if the curvature vanishes, then the curvature of the nabla star is automatic. Always the vanishes, but torsion does not necessarily vanishes even if the torsion of the nabla star vanishes. So this is not necessarily dually flat, but in some sense partially flat spaces. So in this case. We define this function like this. This is from the this observation. Then the same form. We define this function in the same form. Then this gives a pre-constant function on U, and induces the original Riemann metric and the Dirac affine connections. So we call this the canonical precondition function. In the dually flat spaces, it is well known that projection seldom holds. And in the case of the partially flat space, we can obtain the similar, in a sense, generalized projection theorem. Generalized projection theorem is given this in this way. Okay, so now N is a submanifold of U, and then the number geometry starting at Q is also equal to N at point P is equivalent to the equivalent to these conditions. And this is just a corollary of this definition, because this precondition function is defined in this way, so we can easily derive these statements. Okay, and this is this is just a research memo, and Dr. Kose in this propose a similar type of projection theorem in terms of the fine differential geometry, but I think this is equivalent, but the representation is different. Okay. Okay. Now it is well known that exponential family is a dually flat, and the maximum likely estimator in the exponential family can be seen as also projection of the M geodesic. But so I imagine that similar picture. I imagine that similar picture we can obtain the same picture, because that is estimate the solution of this function is also maybe a awesome projection can be understood by the generalization projection theorem. But at the moment, I don't know the statistical meaning of the this geometrical structures. It's a future problem. Thank you very much.